In this module, we'll start to look at those phase diagrams and the energy involved in changing between phases for a sample. So we should all be familiar with what a phase change is in general, right? Everyone in here has observed a solid ice cube melting and becoming a liquid, and we've all taken liquid water and we've heated it up on the stove to make some pasta. In the process, right, you've boiled some of that water away. So we've all gone through the liquid to the gas phase transition, which is the vaporization process, taking something from a liquid into the gas phase. So on the way up, going from a solid to a liquid and a liquid to a gas, those transitions are endothermic. They require the input of energy. That's how an ice cube cools the water down, right? It absorbs the energy from the surroundings. It cools down your water in the process of melting that ice cube. That's why we have to heat the water on the stove to boil that water, because we have to put energy into that sample to vaporize that water, taking it from the liquid phase into the gas phase. And because on the way up, that's endothermic, the way down needs to be exothermic. We need to release that energy. So on the way down, going from a gas to a liquid, that is our condensation. And certainly taking a liquid into the solid would be going through freezing that sample. We can also do both of those transitions all at once. And so on the way up, that is sublimation, going directly from a solid to a gas. So something like dry ice, right? Solid carbon dioxide does that. Or deposition would be going directly from the gas to the solid and skipping the liquid phase altogether. But again, on the way up, going from a solid to a gas is endothermic, which makes the way down, going from the gas to a solid, exothermic. So let's take a look at the first transition, the heat of fusion, and that's the energy required to take a sample from the solid phase into the liquid phase. And that's represented in the chart below as the little red bar. So here's the heat of fusion for butane. It's approximately 5 kilojoules per mole. Diethyl ether is a little bit higher. It's 7. Water is approximately 6. And then mercury would be 23 kilojoules per mole, required to take those from a solid into the liquid form of that molecule. The next is the heat of vaporization. The heat of vaporization is the next transition, so the energy required to take a sample from the liquid phase into the gas phase. And that's represented by the blue bar down here. And so we see here's the heat of vaporization for butane, 24 kilojoules per mole, diethyl ether, 29 kilojoules per mole, water, 41 kilojoules per mole, and mercury is 58 kilojoules per mole. More importantly than those values that I just rang off are the difference between the heat of fusion and the heat of vaporization. Let's just take a look at water, for example. The heat of fusion is 6 kilojoules per mole. The heat of vaporization is 41 kilojoules per mole, right? A little bit more than 6 times greater energy is required to go from the liquid phase into the gas phase. So why would that be? And that's true for all the samples here. For all the samples here, the heat of vaporization is larger than the heat of fusion. Why is the heat of vaporization for a substance larger than its heat of fusion? So the answer to that question goes back to our intermolecular forces that we have to break. If I'm going from a solid to a liquid, the molecules in that sample are still relatively close together. I'm still taking advantage of those intermolecular forces. However, if I go from a liquid to a gas, now I need to break many more of those intermolecular forces because that sample now, the molecules are farther apart So because I had to break more of those intermolecular forces, I had to put a lot more energy in, and hence my 41 kilojoules per mole for the heat of vaporization. So it's a larger energy due to the extra energy required to break more intermolecular forces. If I had that cup of liquid water and I took that cup of liquid water and boiled it all into gas, the volume of that sample would expand immensely. It would expand to fit the volume of the room that you are in. So I would take that sample that once occupied 1 cup, and it would suddenly occupy the volume of the room. A giant increase in the volume of that sample. That means I'm pulling those molecules very far apart, and that means I have to break all the intermolecular forces that were previously holding that sample together in the liquid phase. The next energy is the heat of sublimation, and that's simply just the energy required to take a sample from the solid phase into the gas phase. Right, we're going to skip the liquid phase altogether, and if we take a look at a few of these, right, let's take a look at butane. My heat of fusion is 5, my heat of vaporization is 24. 5 plus 24 equals 29. If we take a look at these two here, I've got 7 and 29. 7 plus 29 equals 36. And the same thing here. I've got 6 and I've got 41. That equals 47. So for those cases, we see that the heat of sublimation is equal to the sum of the heat of fusion and the heat of vaporization. So why is the heat of sublimation equal to the sum of the heat of fusion and the heat of vaporization? The answer to that question is because the heat of sublimation involves going through both steps at once. We go through from the solid to liquid, then liquid to gas. So it's going to be the total energy that was required of doing that process, even though we're only doing it in one step. So we're going through both steps, but we're doing it in one step. We still need to go through that change in energy. So both steps, right, solid to liquid and then liquid to gas, are being done in one step. So that's why we need the energy. The overall energy needs to be the energy that was required to melt that sample, and then the energy that was required to boil that sample, because we're doing both of those things when we go directly from the solid phase into the gas phase. And so here's a heating curve for water, where we're taking a look at the energy required to go through that melting transition, right, the heat of fusion and the heat of vaporization, and putting that together in this graph. So if we take a look at this heating curve, we see that the temperature of the substance does not change during a phase change, right? The temperature does not rise. And so here, if we take a look, I'm ice at minus 25 degrees. I'm adding heat as I go across the x-axis, and as I'm adding heat, I increase the temperature all the way until I hit 0 degrees. Then at 0 degrees, I notice a plateau between B and C. Similarly, once I get to C, I keep putting energy in and my temperature goes up, it goes up, it goes up until I hit D at 100 degrees. And then again, I hit another plateau where I keep adding energy to the sample, but the temperature of the sample plateaus until I hit point E, And then at point E, then the temperature of that sample can begin to change. So why, within this heating curve, does the temperature of a substance plateau during a phase change? Where is that energy going? So the answer to that question is all the energy, like let's think about what's happening during that phase change. At B, I'm ice at 0 degrees Celsius. And then I go all the way over to C, now I'm water at 0 degrees Celsius. So all that energy that went in, right, it didn't go to temperature change because all of the energy during the phase change went to breaking the intermolecular forces within the sample. I have ice at 0 degrees, and then I have water at 0 degrees, right? I had to break some of those intermolecular forces to go from solid ice to liquid water, and the same thing would happen as I transition from D all the way to E. At D, I'm water at 100 degrees, and at E, I'm water vapor at 100 degrees Celsius. So all the energy that you added during that transition had to go into breaking the intermolecular forces that were holding that sample together in the liquid phase. Once you broke all those intermolecular forces, you converted the sample completely from a liquid into a gas. Then an increase in temperature could occur because now the energy you're putting into the sample can go to increasing the average kinetic energy or the temperature of the sample, as opposed to changing the phase of that sample and changing and rearranging the intermolecular forces of that sample. So putting that information together in this heating curve, I'm trying to figure out the energy required for each step of the process. We're going to have a few different calculations involved. And so for the first region, well, I'm taking a solid sample and I'm heating that solid up from minus 30 degrees to 0 degrees. I would want to use Q equals mc delta T, where Q is the energy required to heat the mass of the sample that I have times what's the specific heat of that sample and what temperature change am I going through with that sample. The next calculation, once I've taken that sample all the way up to its melting point, right? The ice has now reached its melting point. The next calculation would be Q equals the number of moles of that sample times what is the energy of going through that process? What is the heat of fusion for that sample, right? That energy is in kilojoules per mole, so I need to know how many moles of water do I have times the energy required to take that water from solid ice all the way to liquid water at 0 degrees. Now that I've melted that sample and I have liquid water at 0 degrees, I'm back into Q equals mc delta T, where Q would tell me the energy required based on the mass of water I have, the specific heat of water, and the temperature change that I'm taking that sample through. So in this case, 0 degrees C to 100 degrees C. Once I've taken that water from 0 to 100 degrees Celsius, the next calculation for that energy would be the energy of vaporization. So now I'm back to how many moles of that sample, right? Because that energy of vaporization is kilojoules per mole. I can find that process based on how many moles I would have, and then the last calculation would be back to Q equals mc delta T. What's the mass of the gas, the specific heat of water vapor, and then what temperature change do I plan to do with that sample? So in order to find out the total change in energy for this process, I would need to know how many of these steps am I going through, and I would need to add together, right? It'd be a cumulative energy, the cumulative energy from region 1, 2, 3, 4, 5, or wherever I'm stopping in this process. So we'd have a few different calculations with a few different numbers, whether we're using the heat of fusion or we're using the specific heat of the liquid or the solid or the heat of vaporization. But at the end of the day, we need to know that cumulative amount of energy for the total transition that we're going through. And so because we're in the middle of a heat wave and then we're in the middle of summer and some of us might be enjoying the benefits of air conditioning, I thought I'd go over some of that energy and what we do with that energy of phase transitions. And that's how air conditioning works. So air conditioning has a few different hydrofluorocarbons within the compressor, and we take advantage of phase changes of that sample to allow an air conditioner to function. And so if I go from a liquid to a gas, that is evaporation and that is endothermic, that absorbs energy, right? So what we do is we take that hydrofluorocarbon, we pump it through the system, and we compress it. It's a liquid, and then we let it inside the house. Inside the house, we decrease the pressure, allowing that sample to go from the liquid phase into the gas phase. That's endothermic. So we blow air through that, and because that process is endothermic, it absorbs the energy from the air. And so it cools the air down as we allow that gas to expand. After the gas is expanded and it's absorbed energy from the house and cooled the air and blown cool air in through your house, we then run it through a compressor that puts energy in and it compresses that gas back down to a liquid. And that process is exothermic. That process releases heat, and so we put energy in to compress that back down to the liquid, and we blow that. That's now outside of your house. And so the unit, the air conditioning unit that you see outside of your house, that's this process right here. We're taking a fan and we're blowing that energy that's released when we compress that gas back down to a liquid, we're blowing that outside of our house, right, to take that energy away from our house. We then take the sample, now that it's compressed and it's back into the liquid phase, we run it through the expansion valve again and allow it to expand within our house, absorbing energy from our house. And we let that cycle go on and on and on, again, removing the energy from our house and taking it outside, cooling the air within the house. So it does not take air from outside of the house, cool it, and then blow it inside of your house. It simply just recirculates the air within your house, but taking some of the energy out of that through this evaporation process and absorbing the energy from that air. And so we could calculate the energy required, right, to go through these transitions, to go through these heating or cooling processes by using Q equals MC delta T, where that specific heat, it depends on the substance. And so we could use water, for example, right? Water has a very high specific heat. All we really need to know to find the energy change required to heat or cool something down would be what is the mass of the sample that I have times the specific heat of the sample, and what temperature change do I want that sample to go through. Again, being aware that this specific heat is going to be specific to the sample we're working with. It could be very high in the case of water, or it could be very low in the case of metals like iron, aluminum, and mercury. And so here's a question for you, question 11.55. Determine the amount of heat required to convert 65.25 grams of solid calcium at 651 degrees Celsius into liquid calcium at 951 degrees C, given that the melting point occurs at 851. So we have to go 100 degrees beyond the melting point. I've provided the specific heat of the solid, the liquid, and then the delta H of the fusion process and the vaporization process. But we won't need this last one. We won't need the heat of vaporization because that's the energy required to go from the liquid phase into the gas phase, and we are not vaporizing that sample. We end at a liquid at 951 degrees Celsius. So taking a look at the calculations that we have to do, I'm starting off with solid calcium at 651 degrees Celsius. I need to heat that up to the melting point. So I need to heat it up to 851 degrees Celsius. And for that, I'll need Q equals M mc delta T. The second calculation, now I have solid calcium at its melting point. I need to go through the phase change. I need to take that to liquid calcium at the melting point, and that's our phase change. And for that, I'll need Q equals how many moles of calcium do I have times the heat of fusion for calcium. Finally, now I have liquid calcium at 851. I need to take liquid calcium at 851 degrees Celsius and warm that up to 951 degrees Celsius. And now I'm going to be back to Q equals mc delta T, except for this time I'm going to use the specific heat of the liquid calcium and not the solid calcium that I used in step 1. So step 1, I've got calcium at 651 degrees. So Q equals my mass of calcium, 65.5 grams of calcium. The specific heat of solid calcium is 0.65 joules grams times degrees Celsius. And my temperature change is 651 to 851. My temperature change is 200 degrees Celsius. So my energy for warming up the solid calcium from 651 degrees Celsius to 851 degrees Celsius is approximately 8,482.5 joules. Step 2, well, I can find out how many moles of calcium I have, right? Moles equals grams over molecular weight. So I have 65.25 grams of calcium, and I know that for every 1 mole of calcium, I would need to have 40.78 grams of calcium for approximately 1.63 moles of calcium. So Q equals a number of moles, 1.63 moles of calcium times the heat of fusion for calcium, which is 9.33 kJ per mole. So this step will require approximately 15.22 kilojoules of energy. Now I've gone through the phase change. Now I have liquid calcium. Now I need to take that liquid calcium from 850 all the way up to 950. So one more 100-degree temperature change. My mass is still 65.25 grams. Now I want to use the specific heat of liquid calcium, which is 0.77 joules degrees Celsius, times my temperature change, 100 degrees Celsius. The energy required for the third step is approximately 5,024.25 joules. So now I have the energy of all 3 steps. The one thing you should notice is that I have 2 different units of energy. I have joules for step 1 and 3, and I have kilojoules for step 2. Taking a look at the question, we want to determine the amount of heat required in kilojoules for this process. So step 1 was 8,482.5 joules, and I know that there are 1,000 joules in 1 kilojoule. So that brings me to 8.483 kilojoules. Step 2 was already in kilojoules. That was 15.22 kilojoules. And step 3 was 5,024.25 joules. Again, divide by 1,000 to go from joules into kilojoules to determine that step 2 was approximately 5.024 kilojoules. Add all 3 of those steps together to get the overall process of approximately 28.73 kilojoules of energy would be required to take solid calcium at 651 degrees Celsius, go through the phase change, make it liquid calcium at 851, and then heat that liquid calcium from 851 to 951. Again, we had 3 separate steps because we had steps looking at just a phase change. we had steps looking at warming a solid, warming a liquid, and the energy for those two steps. Even though we're warming something up, the energy of each of those steps is a little bit different because the specific heat of a solid is different than the specific heat of a liquid.